For today, our topic is control organization. So our what we have to learn is how a control unit of a computer is organized. We know that the control signals in a computer are generated by a control unit, and we also know that the uh, thing that we call the processor that has a arithmetic logic shift unit. It has a small memory unit consisting of various registers of the processor, and it has a third part that is called the control unit. The control unit produces control signals. What could be those control signals? We have studied about a common bus, how we create a common bus using multiplexers. And obviously, we know that a multiplexer will need control lines, selection lines to work. So those selection lines obviously will come from the control unit. In the same way, if we have decoders anywhere or other circuits that need selection lines, control lines, all those lines will come from the control unit. And we have various processor registers, and we know those registers have various control inputs. For example, load is there, clear is there. So these control inputs will also come from the control unit. And also the control unit provides the micro operations for the accumulator. Right? The final after interpretation, after decoding and everything, it gives the signal to the control signal to the accumulator, representing those micro operations, the operation that has to be performed there. And we say that there are two types of control organizations majorly. So on the basis of that, there will be two types of control units. Either it will be a hardwired control unit or it will be a micro-programmed control unit. So the as the name suggests, hardwired control. What does that mean? It means that the manufacturer puts the various circuits, the wiring in such a way, the gates in such a way that upon applying certain instruction, automatically a signal is generated, control signal is generated that selects something, maybe a multiplexer or decoder or like that. So it will be a hardware based unit. So the things are connected, organized by the manufacturer for producing these signals. Obviously, the advantage of this unit will be that it will be fast, because there is no code is to be executed for controlling. Hardware is doing the things, so it will be a fast thing, fast unit. And the disadvantage will be that it is not flexible. We cannot change this. If we want to change, add some more control signals or change some control signals, we need to then do the hardware changes, which obviously are difficult. And there is another control unit, that is micro programmed control unit, and as the name suggests, it is based on program. So there is a particular memory, a segment of memory that we call as control memory. In this control memory, the some programs are there which produce, once we execute these programs, control signals are generated. So if I want to generate a particular control signal, say selecting certain multiplexer or doing some other operation, then we need to first run that program of the control memory, and then that program will produce a control signal which will do the required thing. So before doing any job, we need to run another program that is from the control memory. So that will be a controlling program. So this way, um, this organization is called a microprogrammed control organization, where a program is doing these things. And obviously, this will be a slower than this hardwired control, because we have to run a program for every control signal, and but it will be flexible. If we want to make certain changes in the control signals, we want to put new control signals there, we just have to update the program in the control memory. This here you can see a hardwired control unit. So the first category, the hardwired control unit. So as we earlier said that let us say that a basic computer, we have a basic computer, and in that there is a 16-bit instruction. So here you can see there the instruction has come, it is here in the IR. Fine, it has been read from memory and it is in the instruction register, and the instruction consists of various parts. This is the address part, this is the opcode, and this is the I bit, which decides whether the address is a direct or an indirect address. And obviously this opcode is to be decoded. Fine, so this is 3-bit opcode, so it will be a 3 into 8 decoder. So here we will have a 3 into 8 decoder with outputs from 0 to 7, and all these things, whether the address, whether the outputs of the decoder, the 8 outputs, or the I bit, will go to directly certain hardware. There will be certain gates inside this hardware control unit. The gates will be organized in a certain way by the manufacturer, that they will produce the required control signal. So for example, if there is this D note is on and certain address is there and certain bit of I is there, the gates are connected in such a way that the required control signal will be produced. The various gates will be, the arrangement of the gates will be here, and there will also be timing signals which will be provided, because every single unit in a computer runs on timing signals, clock pulses, and clock pulses are usually generated by a master clock. The master clock generates clock pulses. Same clock pulse goes to every single register in the processor and every other circuit in the processor. But we can control this clock pulse thing like this using a simple sequence counter and a decoder. So if I say I want to keep the clock pulses to 16, fine. So initially, let me say the first clock pulse comes. Initially, this is 0, 0, 0, 0. So let us say the sequence counter is zero, is 4 zeros. Fine. So 4 zeros will go to the decoder, which will produce the first line will be active, that is T naught will be active, all others will be inactive. So if the sequence counter gives 4 zeros, T naught will be active, implying that we are in the T naught clock cycle. So maybe the instruction has just started to execute. So T naught clock cycle will go. The first thing, the fetching will start. Then the next clock pulse, there will be an increment in this sequence counter. It will become 1 in decimal, that is 0001, and T1 will be on, all others will be off. So the next job will be done in the T1. same way with each increment, this will go on from T0 to T15, because with each increment stage will reach when this will become 1 1 1 1, which implies 15. So this will be T15 will be on here, and after that, when an increment is done here, 1 1 1 1 plus 1 will become 0 0 0 0 in terms of 4 bits. So this will be reset. So again, after T5 we will reach T0. So this way, by this simple circuitry, we can control these timing signals going from T0, and we may put an upper limit of T15 here. So at max 15 clock cycles will be 15 timing signals will be generated, and it is not a must that every instruction will require this many timing signals. Say if we have an instruction that requires only 5 timing signals, so this will move from T0 to T5 or T4, fine. And after T4, this clear line will be put on, and this sequence counter will be cleared to 0. So after T4, again T0 will start. So this can be controlled using this clear line. Whenever we want to clear, we can clear, and if we don't use this clear, it will grow from T0 to T15, then back to T0. So this way, these control logic gates can be provided with various timing signals. So this can be visualized as a hardwired control unit, which has a number of gates connected in a certain way, and the gates and also decoders are there, sequence counters are there, and certain flip-flops are there, some registers are supporting it, and this whole hardware organization becomes a hardware control unit. And if we map this timing thing, it will be something like this. Say, so the clock from the clock pulse from the master clock is coming every in a very sequential manner, fine. So let us say the first clock pulse comes, and we know that this rising pulse of the clock pulse will initiate the sequence counter. So the first T0 will be generated here, fine. So the first clock pulse will generate the T0, and this clock pulse runs up to here. So T0 will be from here to here. So in this T0 pulse, certain job will be done. For example, fetching, first phase of the fetch will be done, first step of the fetching of an instruction. Then when the next clock pulse starts, and there will be an increment in the sequence counter, and T1 will be generated. In the next clock pulse, T2 will be generated, then T3, and so on. This will go up to T15 and then back to T0. And if we suppose that we say that our instruction is such that it goes only to T4, after T4 it should be reset, because the instruction, for example, is some, say for example, I have an instruction which is executed by D3. So if you remember that in D3 T4, writing into the memory instruction is executed, right? We have studied this earlier, that at if the D3 line of the decoder is 1 and T4 is 1, is active, that means at that time what happens, storing of the contents of accumulator into memory happens. So whatever is accumulator is stored in the memory, and we know that decoding D3 will be on after T3. It will be on here at T3, and here at T3, And T3, when T3 time cycle is there, we know, we have seen in it in that particular flow chart that at T3 decoding happens. So the decoder produces this output, fine, at T3, and in the next clock pulse T4 the execution will occur, fine. So at D3 T4 the transfer from accumulator to memory will occur, and the same thing will reset the counter, because this transfer will occur and the instruction execution is complete. Now when D3 will be active and T4 will be active, transfer of contents from AC to memory will occur. But now we don't need to go to T5 because the instruction execution is complete. We should go to T0 now, again start the execution of next instruction. So for that, this D3 and T4 at the same time produces a clear sequence counter signal. At the same, this will initiate a clearing of the sequence counter, right? So this thing, this CLR. So that means when D3 will be active from here, fine, and T4 will be active from here, and a certain job will be done. At the same time, there will be an AND gate here, which the output of that AND gate will go to here, clear. Right? This is how the organization is done. So there will be AND gate here because the AND gate of D3 and T4 will be 1. So 1 will go here and this will be cleared. So the next clock pulse will not be T5, it will be T0. Another control organization could be that we call as a microprogrammed control organization. On that basis, there will be a control unit that we will call microprogrammed control unit. As the name suggests, that it is a control unit where the control signals are generated by certain program that we call as a microprogram, and that microprogram will be made up of some instructions called micro instructions. They will decide which control signal is to be generated at a certain time. And if so we say that a control unit whose binary control variables, that is a certain bits are there with certain variables, and those are stored in memory. So they are stored in memory. This is called a microprogrammed control unit. So the control variables obviously will be binary. It will be a set of ones and zeros, and of that set will be called a control word. Control word. This control word, this word will be in there in the control memory. And what is control memory? It is the certain part of a memory in the system that stores only microprograms, those programs which assist in generating control signals. So the computer which has a microprogrammed control unit will have two memories. One will be the main memory for other things, and there will be another memory that will store this thing, micro programs, and that we call as control memory. In that memory, one word will contain that one word will be called a control word, and it will be a micro instruction. So one word of the control memory will be the control word, which will be actually a micro instruction, a set of bits which represent a micro instruction. And this one micro instruction may specify one or more micro operations. So in one word, there may be one or more micro operations there, and a sequence of these micro instructions that we will call a micro program. Fine. So number of micro instructions, a set of micro instructions will be called as a micro program. And this control memory is usually a ROM, read-only memory, fine, because they are kept there in a read-only mode, and then the job is only to produce control signals. And here we can see a microprogrammed control organization. That how does it work? There will be a control address register. Right? So since we are talking of a separate memory unit which is called control memory, and we have to manage this memory, we have to take instructions, micro instructions from this control memory. Fine, we have to fetch that, then we have to decode those micro instructions, and all this is different from the general instruction thing. So this is whole, this memory, this fetching, everything is here related to the generation of control signals. Right? So that is why it will have a separate control address register. So inside that control unit there will be a certain register called as control address register, and the that will contain an address. This address will be of control memory, and when we go at that address we will find a word there that is called control word. When we will fetch that word, that will be transferred to the control data register. So there will be a data register inside the control unit that will be called a control data register. That word will be transferred to that place. Now when one fetch is done and we want to now fetch the next micro instruction from the control memory, for that we need a certain next address, and this next address generation is also a certain uh, job there, and it follows a certain process to generate this address, next instruction, next micro instruction address. And that thing which generates it, we may call it as a sequencer, next address generator, or a sequencer. It may be that if the current address is, for example, 50, next maybe 51, so the sequencer may do a increment and done. It may be something like a branch is there, right? Or a jump is there, like that. So this we need to, let us first see how this happens. So this next address generation happens. So to generate next address, these capabilities should be there, because we know that if the current address is something, maybe the next address is produced just by an increment. This may be generated by there may be four ways. It may be that the previous address is just incremented by one and we get the next address. It may be that there is a branch, conditional or unconditional, that will depend on status bit that we will see later. And there may be a general mapping process, that we have an instruction and we generate this from it, right? This address of control memory from the actual instruction which is there, which is done using the opcode part of that instruction. Then there may be a something like we have a subroutine call, and now we have to return to certain address. This is also a possibility, and this may be depicted in a flow chart like this. So there may be four possibilities. So the address in the control address register will, it will go their address, but this address will be generated from four different ways, and four different possibilities are there. So that means we need a multiplexer here, 4 into 1 mux. What will be the four possibilities? It may be that the address is generated just by an increment. So if the previous address is 50, the next will be 51. So one way is this. Another way is that we have an instruction being executed in the computer. Instruction has an instruction code which has an opcode there. From that opcode, we do certain mapping logic and we find the address of this control address. For that certain instruction, what should be the control signals? That will be decided by that opcode thing. That way we can also produce the address. Second way. The third way is that, for example, there is we took an address, we got to control memory, and control memory will give us certain micro operations, fine, and it will also give us a certain address. This is also possible that this word will tell us, control word will tell us that the next address which you have to go is here. The branch address may be given by the micro instruction itself. This will be the third thing. Fourth is that maybe we had a call to a subroutine, and once we call that subroutine has been executed, fine, and now we want to return back. So that returned address we may have stored in a subroutine register. So in the control unit we will have a subroutine register which will store the return address. And the fourth way will be that this return address will be the next address. So the next address generation may be done like this. So the next address may be of one of these four, right? But which of these four is to be selected depends on the status bits of a control word. So a control word will be here. In the control word, there will be micro operations, there may be address, and there will be certain status bits. Those status bits will check those status bits, and those status bits will tell the multiplexer which of the four it has to pass on. Right? Status bits may be from this control word and it may be from outside also. So it may be for example, checking status whether the accumulator has a 0, whether the accumulator has a positive number sign bit. What is the sign bit? It will be like that. And this way we can generate the next address. This is generation of next address for control memory. Now let us take an example here. So you can see here, this is an example system where we say that we have a control memory of size 128 into 20. Fine. So the size of control memory is 128 into 20, which means that the word size is 20 bits. Fine. And there are 128 words at max in the control memory. And let us say that our main memory is of this size 2048 into 16. That means the main memory, in the main memory one word is 16 bits, and this is the total number of words that may be in main memory. And if this is the control memory, that means there are 20 bits in one word of control memory, which is called control word, which is the micro instruction. So we draw it like this. So what is this? These are the 20 bits of a control word. That is, these are the 20 bits of a micro instruction. And this micro instruction contains 6 parts. Right? This is a general format of a micro instruction. It contains 6 parts. One part is address. This address obviously will be of control memory. The control memory is 128 rows. That means 2 raised power 7. That is 7 bits of address will be there. Right? So this is 7 bits address. And the remaining is distributed like this. There are 3 functions. Fine. So 3 functions can be there at max in a micro instruction. So they are denoted by F1 3 bits, F2 3 bits, and F3 3 bits. And there is also CD 2 bits and BR 2 bits. BR represents the branch field and CD represents the condition for that branching. Right? So this will decide which uh, branching will happen. The conditions will be checked here because of these bits. What we have to check, which condition we have to check, will be decided by these bits, and this will be the branching thing. And since this function is of 3 bits, it should represent 8 micro operations, but in actual it represents only 7, because 3 bits 0 0 0, it means no operation, right? So that means this F1 represents 7 operations, F2 again represents 7 operations, and F3 also 7 micro operations. So in total there will, if we combine all, that will be in total 21 micro operations. So in total, in this format, 21 micro operations can be performed, and at a time there will be 3 micro operations, right? And at maximum there will be 3, minimum can also be there. So for example, if this is 000, that, and this is some value 110, this is 101, that means there are only 2 micro operations. 000 means no operation, right? This what I just said can be depicted here, right? So we can see it here. So all the fields which these 5, F1, F2, F3, CD, and BR, here we can find table for each. And so for example, if we look at F1, F1 is 3 bits. 3 bits will have 8 combinations. Each combination has a meaning. You can see the corresponding micro operation as well as the symbol here. So if this is 000 F1, it will mean no operation. And this, if F1 is 001, it will mean add, fine. So the contents of AC will be added to DR and stored in AC, the result in AC. And next 010 means clear AC. Next is increment AC. Then DR to AC. Contents of DR will be copied to AC. Then DR to TR, DR to AR. That is the contents of DR data register will be transferred to address register. Right? And we know, we just said that in our example, the main memory is of size 2048 into 16. So 2048 means 11 bits of address. So that's why it is written here 0 to 10. So 11 bits of address. In the same way, this 110 will be PC to AR, and 111 means write operation. That is, the contents of DR are written into memory, main memory. In the same way, then we have F2. 000 means no operation. 001 means subtraction. Next is OR, then AND, then read, then AC to DR, then increment DR, and then PC to DR. In F3, 000 means no operation. 001 means XOR between these two. Then next is complement AC. Next is shift AC to the left, then shift right, then increment PC, and 110 means AR to PC, and 111 is a reserved. Then the next field is CD of 2 bits. 2 bits means 4 combinations, and if CD is 00, it means it is an unconditional branch, right? So CD decides which type of branch it is. What is the condition for that branching? So if CD is 00, it means it is an unconditional branch. Just go to that location, just branch. Otherwise, it is a conditional branch. If it is a 10, it means you have to check this I bit. Fine. Since it is 16 bits in the data register, because our main memory is 2048 into 16, so data register will have 16 bits. So we have to check the most significant bit, and if it is 1, then it is an indirect address bit, what we call as I bit. So it means check the I bit before branching. Then if it is 10, it implies check the sign bit of AC before branching. If it is 11, it says check whether AC has a 0 or not before branching. So CD puts the condition to the branch. Then another field is BR, which means the branch. Again, it is 2 bits, so there will be 4 combinations. If BR is 00, it means jump to certain address. So the corresponding micro operations will be like this for jump. Right? So, and if it is 01, it means call certain subroutine. Right? When we call certain subroutine, these operations are performed. Then if it is 10, it means return, means we are returning from a subroutine, so we will take the return address, that is the next address. And if it is 11, then it is the mapping, that is that we saw earlier in the flow chart. 11 here means that the address you have to, next address you have to take through mapping of the opcode of the instruction code. So we will have this 11 to 14 bits will be instruction, that code. So that they need to be taken, and they will be mapped and give us the next address. Others will be put to other things to 0 here. So these 5 tables are representing how this the binary values in here, what do they mean, what do they represent, what will they do. If I have a micro instruction of this certain bits, and what will happen by these 3 bits, what will happen by these 3 bits, and so on. This is about microprogrammed control organization.